My name is Ksip Lms, lecturer in mathematics, working in PR Government Degree College, Kakinada. My PPT presentation is orthogonal and orthogonal set in an inner product space. Definition by orthogonal. Let alpha, beta be vectors in an inner product space V of f. Then alpha is said to be orthogonal to beta if inner product of alpha beta is equal to 0. For example, if alpha is equal to vector 1 comma 1 comma 1 and beta is equal to another vector 1 comma 0 comma minus 1, inner product of alpha beta is equal to dot product is equal to 0. That means inner product of alpha beta is equal to 1 into 1, 1 plus 1 into 0, 0 0 plus 1 into minus 1 is equal to 0. We can easily observe that x-axis is orthogonal to y-axis and y-axis is orthogonal to x-axis. Note A, the relation of orthogonal in an inner product space is symmetric. That means inner product of alpha beta is equal to 0. That implies inner product of beta alpha is equal to 0. Therefore, beta is orthogonal to alpha. Note B, if alpha is orthogonal to beta, then any scalar multiple of alpha is also orthogonal to beta. That means inner product of k alpha comma beta is equal to k into inner product of alpha beta is equal to k into 0 is equal to 0. Therefore, k alpha is orthogonal to beta. Next point, the 0 vector is orthogonal to every vector. That means inner product of 0 alpha is equal to 0. Inner product of 0 beta is equal to 0. Inner product of alpha 0 is equal to 0. Now we are going to see the theorem on orthogonality. The vectors alpha and beta in an inner product space are orthogonal if and only if norm of alpha plus beta whole square is equal to norm alpha square plus norm beta square. Proof. Let alpha and beta are vectors in an inner product space V of f. That implies norm of alpha plus beta whole square is equal to norm alpha square plus norm beta square. Norm of alpha plus beta whole square means inner product of alpha plus beta comma alpha plus beta is equal to norm alpha square means inner product of alpha alpha plus norm beta square means inner product of beta beta. If and only if multiple of alpha with alpha plus beta. That means inner product of alpha alpha plus inner product of alpha beta plus multiple beta with inner alpha plus beta. So inner product of beta alpha plus inner product of beta beta is equal to inner product of alpha alpha plus inner product of beta beta. Cancel both sides, inner product of alpha alpha plus inner product of beta beta. If and only if inner product of alpha beta plus inner product of beta alpha is equal to 0. If and only if inner product of alpha beta plus inner product of alpha beta is equal to 0. Alpha beta are real number in an inner product space. Real vectors in an inner product space. If and only if 2 into inner product of alpha beta is equal to 0. 2 not equal to 0 kabatti if and only if inner product of alpha beta is equal to 0. And if and only if alpha beta are orthogonal. Definition orthogonal set. By definition of orthogonal set. Let V of f be an inner product space. A non-empty subset S of V is said to be an orthogonal set if any two distinct vectors in S are orthogonal. ORR. Let S is equal to alpha 1, alpha 2, alpha 3, so on alpha n is orthogonal subset of an inner product space if inner product of alpha I, alpha j is equal to 0 if I not equal to j, and alpha I, alpha j is equal to 1 if I is equal to j in V of f. Now we are going to the theorem on orthogonal set. Every orthogonal set of non-zero vectors in an inner product space VFF is linearly independent. Proof. Let S be an orthogonal set of non-zero vectors in an inner product space VFF. Let S1 is equal to alpha 1, alpha 2, alpha 3, so on, alpha n be finite subset of S contains n non-zero vectors. That implies a1 alpha 1 plus a2 alpha 2 plus so on plus an alpha n is equal to 0. Let 0 vector is equal to inner product of 0 comma ak. That implies inner product of a1 alpha 1 plus a2 alpha 2 plus so on plus an alpha 1 comma ak is equal to 0 vector. 0 vector means 0 bar comma ak. That implies a1 into inner product of alpha 1 alpha k plus a2 into inner product of alpha 2 alpha k plus so on plus ak into inner product of alpha k plus so on an into inner product of an alpha k is equal to 0. So any two distinct vectors are 0. S1 is a orthogonal set kabatti any two distinct vectors zeros అయిపోతున్నాయి కాబట్టి alpha inner product of alpha 1 ak 0 అవుతుంది, inner product of alpha 2 alpha k 0 అవుతుంది and so on inner product of alpha n alpha k is equal to 0. Inner product of alpha k not equal to 0 ఎందుకని అది norm of alpha k whole square అవుతుంది. That implies a1 into 0 plus a2 into 0 plus so on ak into inner product of alpha k plus so on an into 0 is equal to 0. So that implies ak into inner product of alpha k is equal to 0 bar. That implies ak inner product of alpha k ante norm of alpha k whole square is equal to 0 vector. So that implies ak is equal to 0 bar. So ak is equal to 0 indante a1 0, a2 0, a3 0, so on an 0. All scalars are 0. Therefore S1 is a linearly independent set. Again therefore every finite subset of S is a linearly independent set. Again therefore S is a orthogonal set kabatti every orthogonal set of non-zero vector in an inner product space V of F is a linearly independent set. Thank you.